All right, Jihad, it's just you and me. Chapter ready. If you take this, which is chloroform, and analogously say the bromine equivalent of chloroform would be called bromoform. If those get treated with base, like KOH, the first thing that happens is this H is going to get ripped off. That makes this carbanion species. What would the corresponding chlorine molecule look like? And how would it happen? So let's address that. So if we put up there chloroform, and we have hydroxide, which is a base, because this C has these electronegative Cl's, it's relatively more acidic than a normal CH bond. And that means that base can grab that H, and those electrons can go back to the C. And then you have that C, which has 3 Cl's and an extra pair, so it's thus a negative charge. And of course, this H as a proton on OH makes water. And then the interesting thing is this species has 3 good leaving groups. And any single one of those chlorides can leave. And if it leaves with that pair of electrons, then do we get to that weird species, which is called a carbene. Carbenes are useful nucleophiles. So why might a carbene be a nucleophile? Because the carbon has pairs of electrons that can act as negatives, but is the carbon formally negative? No. So in your understanding of what makes something a base versus a nucleophile, of course, if it is negative, it's more nucleophilic than if it isn't, but that also tends to make it more basic. So that's why carbenes are useful nucleophiles. So that's one of the reasons why, like when we're doing extractions with dichloromethane, should we ever treat that with a strong base like KOH or NaOH? No, because these H's can get ripped off, and then you can form that, which again is a carbene, and then can that carbene start doing nucleophilic reactions while you're in your separatory funnel? So when we made our ester, did we do exactly that? Yes. But when we basified, did we get it to pH 14 where we had lots of hydroxide around? Or did we try to get it just to pH 9 or 10? We tried to. I think we succeeded because was our yield of ester pretty good? Yes. So that's a little segment in chapter 8 entitled Carbenes. And next up would be ozone. So if you treat an alkene with ozone, you get what's called oxidative cleavage. So if you look at the products, what does it mean, oxidative? Or why is it called oxidative cleavage? Well, if you look at O3, does it have lots of oxygen? And is O3 an element of oxygen? And it's called ozone. And if you look at that alkene, would you say symmetrical or asymmetrical? In other words, is that matched by that? Or do the ene carbons have different groups on it? So it's asymmetrical. And most importantly, this carbon has two carbon groups on it, or a carbon group and an H. Because we're going to say R's are carbon groups, and that's, of course, an H. Could this be an R? Yes. Would the product's composition change? So if we add ozone to an alkene, we chop the alkene in half, and do we add an O to this carbon? And do we add an O to that carbon? So is it pretty straightforward on how or what you get? And since you're practicing your functional groups every night, what two functional groups did we just create? No. Yes. A ketone and an aldehyde. No ether. Which one's the ketone? Which one's the aldehyde? If this were an R group, then what would we generate? Two ketones. So do you get two molecules from one when you do an ene reaction with ozone? All righty. And we're not going to go through the mechanism. It's really interesting. If you're interested, it goes through an ozonide. Ozone is going to look like that with its 18 valence electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18. And then the ene's going to attack it to make a cyclic structure. And then the O's rearrange and insert themselves into that C and that C. So for testing purposes, you're not responsible for knowing the mechanism, but you are responsible for knowing O3 is what? Ozone. And ozone plus an alkene makes aldehyde ketone, or aldehyde aldehyde, or ketone ketone, depending on what groups are on your ene. And this is certainly not to be confused with that. So if I say this is the same ene, but a very different product. So this is called oxidative hydroxylation, or oxidative dihydroxylation, or for short, just dihydroxylation. So do we see why it's called dihydroxylation? Because what do we add to both carbons of the ene? OH. Are we going to be responsible for the mechanism? No, but this is osmium tetroxide. You could think of it like osmium with a whole bunch of O's. And It flips around and this C and that C both attached to O's. And then when we work it up, we protonate. And if I say this or that, what's that mean? Either reagent would make that happen. So do you need both or either or? And which one to you seems more exotic, osmium tetroxide or potassium permanganate? Osmium tetroxide is a lot more expensive, a lot more exotic, and if you would guess, a lot more efficient. KMNO4 is an older school oxidation reagent. It'll work sometimes, but it won't work as well as osmium tetroxide. So if you have big pockets, what do you use? Osmium tetroxide. If you don't have a lot of money, what do you try? And then if it doesn't work with KMNO4, you take, borrow, or steal osmium tetroxide because that'll help you get it done. That's a classic example would be if I have that ene, which we call ethylene, correct? Then what would be this product? It would be that. What might you call that? There you go. Ethane diol. And when you get these polyols, they go by the name glycol. So now if we sort of piece that together, what's the common name for ethane diol? Ethylene glycol. Then where would we find ethylene glycol? On the board. Very good. That would be what's in a car radiator that acts as antifreeze. So a lot of these reactions have historical precedence in what they made, but then they also have synthetic relevance because we can do lots of things with diols. So how do you not confuse this with that? Come to class and study. One makes cleavage, one just adds OH and OH. And then we're over to what's called halohydrin formation. So halohydrin, what we're going to add across the double bond is OH and then one of your halogens, either Br, Cl, or I. So in my example, I'm using bromine. And what's the other reagent besides bromine? Water. So if you recall, what would happen if there were no water? Angela says she really wants to review that. So if there, well, I'll just use that. If there were no water, what do we get? Bromination, where we add one bromine to each carbon of the ene. And by what mode would that happen by? Stereoselective, stereospecific, random, carbocation-like intermediate, or we don't remember it. So we're going to do that. And we're going to do do that, and I'm going to say this represents a bond connection between which carbon? That's a you pick them. So whichever one you pick, what would happen to the other carbon? It would have to become positive. If we don't stop there and say this is going to attach like that, now that's connecting which carbon to the bromine? This one, because this pair is connecting that carbon to the bromine. Now, in the end, will both carbons be connected to the bromine? And if right alongside we do that, what's the result of those three electron movements? Yeah. Somebody's got to be plus. Who is it? So this is where you say, in this starting material, is anything charged? No. Is this making a new connection between carbon and this bromine? Is this making a new connection between this carbon and that same bromine? So this arrow is right there, and this pair is right there. And did this bromine thus gain a pair and lose a pair? So does that affect its overall charge? But what's happening here? This bromine is gaining a pair, that's why it became, but this arrow is saying this bromine is also losing its share of that pair, so who's going to be positive? This bromine. And then when you're doing mechanisms, you try to circle your charge to tell your audience where it is. And that intermediate's called a brominium ion. And then what happens? Now it's really helpful to know where you're going. Hypothetically, you could do that. You could do this. And that would generate and now who would be positive? This carbon. And then what could you do? And if that were the mechanism, then would this bromine have selectivity for one face or the other? Or is this an achiral and equal faces are open to attack from the bromine? So would you expect only one stereoisomer? Or a mixture of the two in equal amounts? But we know it doesn't do that. This attacks as that happens. Why did I make the effort to draw my arrow way around there? It's coming in from the opposite side that this is leaving. So when we're done, are these two bromines random in the product? Or do we get anti-addition, and the product is trans. So what's the stereospecificity? Or what's the mode of addition? Anti. Meaning the two bromines that are coming in end up from opposite faces. And does this have free rotation? No, why not? Because it's part of a cyclic system and it would create torsion, so it prevents it from rotating. But can that chair flip into different conformations? Yes. So that's a quick review because that's what Angela asked me to do. That's a review of just straight up bromination, right? So if I say, is Markovnikov's rule in play? No, why not? Because Markovnikov's rule is going to only be in play when you're adding some reagent that has an H to an ene. And only if the ene has two carbons with different numbers of H's starting out. So is there any regiochemical consideration because of Markovnikov? No. Is there a stereochemical consideration? Yes. And what is the stereospecificity or the mode of addition? Anti, and thus do we get the cis or the trans? Trans. And would you say this alkene is cis or trans? Even though it's technically not either, because that group is the same as that group. This group and that group are on the same side, so it's cis-like. But technically, why do I say this group is the same as that group? Because if you march this way, are they identical? So then it's technically really not cis or trans. If we were to put one chlorine there, now is it cis or trans? Cis, because now the similar groups go in the same direction. And could you draw the trans isomer? Because what would happen if you tried to rotate that? You'd get too much torsional strain. So do alkenes have free rotation? No. So is there a trans isomer of that molecule in existence? No. If I erase that, now is it cis or trans? Cis. And then the product would be what? That. And now would this have free rotation? So would it stay in this anti-configuration or would it rotate to all possible conformations? Does that make it complex enough? All right, back on point. Now, if we're going to, instead of just straight up bromination, we're going to do bromine and water, who do you guess is going to be the better nucleophile when you get to this stage? So you do the exact same thing to start off. Make the bromanium ion. But now you have both bromide with a minus and water. And if you know where you're going, an ene, when we do halohydrin formation, adds what to the two carbons of the ene? Br, and now what do you guess you're going to invoke attacking the brominium ion? The water. So you can think of it as when this bromide leaves, it kind of ties up as HBr. And so then if you want to, can you actually invoke hydroxide as your nucleophile? So that's the fun thing about organic chemistry. If you see this reagent system, can you really choose that as your nucleophile? Yes. Can you really choose that as your nucleophile? Yes. And which one's a better nucleophile? Hydroxide. Which one's also a better base? Hydroxide. Which one's present in water? They both are. Which one's more prevalent in water? Water. But that doesn't mean it's the only thing that is there. So if water has some hydroxide, does it also have some hydronium? So you could invoke any of those. So as far as your mechanism goes, if you want to use straight up water as your nucleophile, is this water going to attack the brominium from this same face or from the back face again? If this is a wedge, then that's a wedge. And this is going to attack at the same time this leaves. Is it SN2 like? And we always say front side attack or back side attack. Backside attack. So will you initially get anti-addition, where that OH2 comes in like that, and that bromine is on the other carbon like that. And who would be positive now? The O of water. And in your last step to get to release your OH, would you just pop off the H, making your alcohol? And if you'd rather use not water, but hydroxide as your nucleophile, then you could just use that, again, backside attack, and then would you get your OH directly? So far, so good with that. Do we have lots of things we can do with halohydrants? Yes. All right, then it gets easier. What would you say hydrogenation adds to an ene? Hydrogen. How many hydrogens? 2 overall. So does one H go on each C of your ene? And do we need a catalyst for that to happen? Yes. And our catalysts are those expensive, usually expensive transition elements like platinum, rhodium, or palladium. And what's happening there is they serve as catalysts. So what the metal does is actually is porous, so it can dissolve hydrogen gas. You take your ene, your catalyst, and hydrogen gas under a good bit of pressure, and the hydrogen gas sort of dissolves into the metal, and then the metal sits down on, I'll just use metal. The metal sits down on the ene double bond into the pi system. And since the metal has hydrogen dissolved in the metal sort of facilitates delivery of the hydrogen to the ink. And then once it delivers the hydrogen, the metal goes back, picks up more hydrogen, and comes back. So is the metal a reagent or a catalyst? Catalyst. So do you need a lot of it? No. Do you need a pressure reactor? Yes. So can we do hydrogenation in labs like this? We could, but we choose not to because we don't like to work with high pressure hydrogenations. They would have to be done in what's called a FOM, which is just like a pressure cooker, stainless steel with flanges, and you bolt it all together and then pour in hydrogen, high pressure. So is that a way to make anes from enes? And then last thing, this is because Angela really wanted me to review that again. Now is Markovnikov in play? And Markovnikov says which C is going to get the incoming H preferentially? That one. And therefore, which C is going to get the BR? That one. And what happens to the double bond when you add to it? It goes away because you've added to it. And is that the product? And is that product primary, secondary, or tertiary halide? Tertiary halide. And is it called the Markovnikov product? So a fun test question is, who's Markovnikov named after? Markovnikov. And sometimes science happens fortuitously. What's that mean? It means someone makes a mistake, but good comes out of it. Fortuitous. It's just a nice word for saying someone probably screwed up. Usually these reactions were probably done in a solvent like ether or THF way back when. Solvents, just as you already know, modify any heat, give your chemicals a soup to swim in so that they don't get too concentrated and do other reactions. So in other words, if we did this, what might happen to this if we didn't have a good solvent to stabilize it? Could it easily form that carbocation? And if we didn't want to form a carbocation, then that would be bad. So could we provide a solvent that helps stabilize stuff? So as a story, ether, when we say ether, we really mean what ether? Diethyl ether. And when you leave diethyl ether exposed to air, air contains oxygen, and diethyl ether and oxygen react slowly over time, and that makes what's called a peroxide. Where you add an extra O into an ether, then you have a peroxide. So that's reminiscent of what you all put on a cut to sterilize it, hydrogen peroxide. So is that a new functional group for you? Sure. Is it hard to remember? Maybe. Just remember ether, extra O is peroxide. So is this diethyl ether peroxide? Is this hydrogen peroxide? and which is more of an explosion hazard? So when we say stuff burns, does ether burn? Yes, very well. It's a class 4 on the NFPA. Does acetone burn? Does methane burn? Do a lot of your hydrocarbons burn? Do a lot of your alcohols burn? Do a lot of ethers burn? Then when you take ether, which burns on its own, and insert another O, and O always supports burning, which would you say is more hazardous? Ether peroxide or just ether? Because it brings more O to the fire, so to speak. So I'm sure way back when somebody was saying, I'm going to do a Markovnikov edition of this ene and make that product. And lo and behold, what did they get? That product. And they scratched their head because Markovnikov ruled for a long time. And Markovnikov says you shouldn't get that product. And is that fortuitous? Yes, because sometimes do we want the anti-Markovnikov product? So my long stories, then you'll be able to answer the question, what promoted the formation of the anti-Markovnikov product? The ene, the HBr, the ether, or the peroxide, which was contaminating the ether? All right, let's review. If I say we're going to do this, then we're going to use fresh ether, freshly distilled ether with no peroxide in it, and we get this product. Would we be happy? Because that's what we've been preaching, our Markovnikov. So if I say, go get the old can of ether and do the same reaction, and you bring me back this product, so was it the ether's fault or the peroxide in the ether? And then what would you do if your professor said, well, you've just broken Markovnikov's rule, and that's been in place for 30 years, and that just simply isn't going to happen. Go try again. So if you wanted to get your name on a paper, you would say, I don't care what Markovnikov said, I got this product. Because then you get to write the paper that says, I now know how to make the anti-Markovnikov halide, which no one else could make before. And how did you come upon your discovery? Fortuitously. So on the MCAT, it's very common to see they won't show you the structure of ether more than likely. They would just say this with ether plus peroxide. So if you see this in ether, what product do you write? Markovnikov. If you see this in ether but plus peroxides, what product do you write? Anti. So in organic chemistry, do we have a way to make either one? Yes. That is chapter 8. So when are we going to have our second test? Friday? Didn't think so. Monday? Didn't think so. Next week or the week after? You get a choice. Next week is the 9th and 11th. The week after would be the 16th. Yeah. So we either have to have it on the 16th, the Monday before the project, or we have to have it next week. Yes, we are. So next week is the 9th and the 11th. Who votes for the 9th next Monday? I think so. Who votes for the 11th? That'd be next Wednesday versus the following 16th, which is Monday. So who votes for the 16th?
What is our next one after?
In December.
Final? So we have one more.
We hope to have one more test. So that means next week we'll be covering new material, but of course, we got sheets to practice, right? So we'll say we're having our tests 2 on the 16th. What chapters is it over? Yes, and everyone's working on those sheets every night. Do you want me to give you homework from the textbook like I did last time? All right, we'll do that. On Monday, we'll be making aniline dye.